In 2012, the arrival of AlexNet proved the power of deep convolutional layers, starting an 8-year stretch where convolutional neural networks were the undisputed standard for computer vision. That dominance lasted until 2020. Google researchers published a paper titled "An Image is Worth 16 by 16 Words," demonstrating that a transformer architecture, originally built for natural language, could be adapted to recognize images at scale. Standard CNNs were eventually replaced in top-tier benchmarks because of a physical limitation. While they are highly effective at detecting visual features, they possess a structural inability to understand global context. This is the long-range dependency problem, the mathematical difficulty of correlating two pixels located at opposite ends of an image. It is a bottleneck that standard convolutions cannot fix. To understand why the industry pivoted, we have to map the geometric limits of the convolutional kernel, identify where the math breaks down in deep networks, and look at the self-attention mechanism that took its place. The field has moved from routing information locally, one small patch at a time, to a system of dense, interconnected routing, where every single pixel can communicate with every other pixel instantly. Understanding the current state of machine learning requires knowing why the localized operations that built the industry are no longer sufficient. An input image passes through convolutions and pooling. Spatial dimensions shrink, while channel depth expands into a 1D vector, trading physical layout for depth. As 3x3 kernel sweeps the image, processing 9 pixels at a time, multiplying and summing them into a single value. This localized math works well for extracting primitive features. By scanning the image through this tiny window, the network can isolate horizontal edges, detect vertical lines, or find sharp corners. After the features are extracted, the network uses pooling operations, like max pooling, to aggressively reduce dimensionality. Max pooling forces abstraction by selecting only the highest activation value within a small window and discarding the rest of the data. A CNN sacrifices the full image view to hunt for localized primitive features within a restricted mathematical window. The receptive field is the total number of original input pixels a single kernel can see at one time. On this 32 by 32 grid, a 3x3 kernel covers less than 1% of the total image. Because the kernel is so small, it lacks global context. It cannot recognize a whole digit. It only sees an isolated curve or a segment of a line. This creates a paradox. The network needs to understand a massive image, but its primary tool only processes 9 pixels at a time. To fix this, engineers stack multiple convolutional layers. Passing a 3x3 kernel over a previous layer's output grows its visual footprint. A single pixel in the second layer now effectively represents a 5x5 patch, or 25 pixels, from the original input. Adding more layers increases this effective receptive field linearly, slowly expanding the network's vision until it eventually spans the entire frame. The only way a CNN can understand a whole image is by becoming deeper. But relying on extreme depth to achieve global context leads to a mathematical breakdown. Creating a global receptive field through sheer depth causes significant optimization problems during the training process. The network learns by adjusting weights based on the loss gradient. But in a 50-layer network, as the gradient propagates backward, it shrinks. By the time it reaches early layers, the magnitude is so small that weights barely change, stopping the learning process. Innovations like ResNet use skip connections to help the gradient bypass layers, but they do not change the localized nature of the underlying architecture. This local focus has a direct impact on how the network interprets the world. It creates translational invariance, the ability for a network to detect a feature regardless of its physical position on the screen. While this is often useful, it means the network can detect specific objects while remaining blind to their logical spatial context. A filter trained to find a car triggers just as strongly if that car is on a road or parked on top of a skyscraper. The convolutional network has isolated a pattern of pixels, but it has completely failed to understand the actual image. In high-stakes environments like autonomous driving, spatial context is a requirement for safety. If a pedestrian steps into the far left edge of the frame, the vehicle must correlate that information with other visual cues. The pedestrian is on the far left border, while a critical green traffic light is on the extreme far right. This creates a routing problem for a CNN. It needs to logically connect these two features, but they are physically separated by hundreds of pixels. Because the architecture is localized, the data from the pedestrian and the light must pass through dozens of layers before their receptive fields finally meet and allow the network to see them together. This is the same bottleneck that once limited natural language processing with recurrent neural networks. Just as an early RNN would lose the context of the first word in a long sentence, a CNN loses spatial correlation across wide gaps in an image. Vision researchers needed a system that could connect the far left of a frame to the far right instantly, without relying on sequential local steps. The 2020 Vision Transformer provided the architecture to solve this. It discards convolutions entirely. Instead, the image is sliced into a grid of 16 by 16 patches. Each patch is flattened into a vector, effectively turning the image into a sequence of words. By treating these patches as discrete tokens, the model can process an image using the same mathematical framework a language model uses for a paragraph. This allows the network to use global self-attention instead of localized kernels. Self-attention calculates a relationship score between every single patch and every other patch simultaneously. The physical distance between the pedestrian token and the traffic light token no longer matters. Spatial distance is irrelevant because the relationship is established in a single routing step. This global web of attention is more efficient than the deep, decaying sequential layers required by a CNN. By replacing the local kernel with global self-attention, Vision Transformers achieved full context from the very first layer. They solved the long-range dependency problem and changed the trajectory of computer vision.